Well, now we're going to study the ratio test, which is very useful in determining absolute convergence, especially when we have factorials and powers in our expression for an. The test goes like this. If the sum of an is a series with possibly positive or negative terms, we let L equal the limit as n goes to infinity of the absolute value of an plus 1 over an. And if L is less than 1, then I know that the series converges absolutely. If L is greater than 1, or infinity, then I know that the series diverges. And if L is equal to 1, then this test is inconclusive, and I can't figure out whether the series converges or diverges using this test. The test is very useful when you have factorials and powers constant appearing in the terms of your series. Now, if you think about what this test is saying, if the limit as n goes to infinity of the absolute value of an plus 1 over an is L, then as n gets very, very large, the absolute value of the n plus 1th term is very close to L times the absolute value of the nth term. So the series is behaving like a geometric series where r equals L. And of course, if r is less than 1 in a geometric series, the series converges, and if it's bigger than 1, it diverges. So that gives you some rough justification for this theorem. Let's check with the following series, see if it converges. Notice it's an alternating series, so it has positive and negative terms, and to apply this test, I look at the limit as n goes to infinity of the ratio of the absolute value of the n plus 1th term divided by the nth term. And of course, the minus 1's disappear, and we're looking at the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial. And a large part of those factorials cancel, and a large number of the powers of 2 cancel. So we're looking at the limit as n goes to infinity of 2 over n plus 1. And as n goes to infinity, that goes to 0. And this number is less than 1. So by our test, if L is less than 1, then the series converges absolutely. And of course, if a series converges absolutely, we know it converges. So therefore, our series converges. Let's apply the test again. Let's test the following series for convergence, the sum of minus 1 to the n times n over 5 to the n. We're looking at the limit as n goes to infinity of the absolute value of an plus 1 over an, and that's the limit as n goes to infinity of n plus 1 over 5 to the n plus 1 divided by n over 5 to the n. And now we have a lot of cancellation here. After cancellation, we have the limit as n goes to infinity of n plus 1 over 5n. And that's equal to 1 over 5 times the limit as n goes to infinity of 1 plus 1 over n, which is 1 over 5. This is less than 1, so therefore our series converges absolutely.